About them too. You'll see what I mean here in a minute. There's one called Wolfram Alpha. Has anyone ever heard of that? No. Yes. Wolfram Alpha is insane. It's beautiful. 1% of what it does is math, which when you see what it does with math, you'll be like, that's just 1% of what it does. If you're smart enough to get pro access, and then if you're smart enough to remember your password, oh shit, here we go. This might be an interesting moment. Hey, no way. Okay, sorry. Can you guys see that okay? So Wolfram Alpha is one thing, and just really quickly, if I put 4x squared, sure, that looks beautiful, I love that. Oh my gosh. It gives you the graph of it, gives you solutions, step-by-step solution, show all steps, it explains the steps, right? Okay, so that's, you're like, that's nice, Jeff. It's kind of a hard quadratic. Yeah, that's nice. But then you go to examples, and you click on math, and then you go to calculus analysis, and you click on differential freaking equations, and you click on just pick one. There you go. And then this is what's called an initial value problem. We'll be talking about that today. It's a differential equation with certain conditions. Because, of course, when you solve the differential equation, you're going to get at least one constant that defines a family of solutions. Since it's a relationship between the slope and sometimes the values, and to some degree, for some of these, it shouldn't matter where they are, right? So sometimes the C might just control where it is, where it hits the y-axis, for example. And also sometimes the C will actually affect other aspects of the shape. Okay, maybe. Because there could be other ways to have the relationship between the second derivative and the first derivative be the way that it needs it to be. I don't know if you guys are a little bit with me. Later in the semester, you should be a lot more with me. And here, there's the solution, step-by-step solution. Holy shit, show all steps. Well, you're going to love all these steps. Right, okay. All right. Crowd goes, meh. I mean, this is, if used correctly, it's an amazing study tool. If used incorrectly, it's a great way to get homework done. But, again, at this point, you should know the value of homework, so I just wanted to make sure everybody knows I know this exists. And there are certain things, especially when my algebra students try to use this, it'll do like way advanced mathematics to solve something just because that's the more general thing that will work. And then this has actually happened twice. And I'll say, can you explain this part in the middle where you suddenly start using, implicit differentiation and you're in Math 90? Can you explain that part to me? And they're like, it's just something I came up with. No, get out. Get out. And then I show them it's exactly what it says in Wolfram Alpha, and they're like, I'm sorry, they just don't know. But this is just beautiful. You can't beat this shit. And if you've never looked at Wolfram Alpha before, just hit the examples and just go crazy. And look at all the shit it does. Look at all the shit chemistry and physics. Sorry. So, and it's got little Easter eggs too, like what is the meaning of life? And of course, it gives the correct answer, 42. Right? All right, good. Most of you guys got that. I'm surrounded by more geeks than I am in some of my other classes, so that's beautiful. And how many angels can dance on the tip of the pin, all this kind of stuff. It's got a lot of Easter eggs, but it's got a lot of cool shit. The second thing I want to show you, besides Wolfram Alpha, is something called Desmos. Something nice. Does anyone know about Desmos? It's just stupid awesome. I don't want to only show you this. I mean, just to show you very quickly, x squared minus sine x. Sure. Do it. There it is. And then I could put in there x plus cosine. Got it. X. Bam. And then I can see the solutions if that equals that. That's beautiful. That's awesome. That kicks the TI's ass to the curb. There's another thing that a student of mine in my last, I think it was 2 semesters ago, in my Calc 3 class, he did, what was it? Let me see if I remember. plot.ninja. Let's see if I remember correctly. And this is a three-dimensional grapher that kicks the ass of anything. I mean, look at all this beautiful, awesome contour curves and shit. I mean, give me a break. And you can just play around with that shit. I mean, that's awesome. If you're not taking notes on this, I don't understand you. This one I don't think any of you have ever heard of because I haven't really got the word out there much yet, right? So I want to tell you guys about it because it's awesome. And will it necessarily help you in this class? I don't know. We'll have to wait and see. Is it cool as shit? Yes. That's the important thing. All right. So really powerful graphing tools. He keeps making this better and better. There's some new stuff on here that you didn't know about before, but sweet. Okay. So I just wanted to throw all that out there. And then there's even more stuff than this. So I'm open to, if there's something you go to that you use a lot that I might not know about, let me know. And maybe I'll try to make a little collection of tools and repositories of stuff, right? Okay. There he goes. Can you bring the lights back up for me? Thanks, man. Whoa. This is going to drive me crazy. So first off, I don't know, are there any, we haven't really done anything out of the book truly yet. I mean, we sort of did. Anything, questions from the first class left over? Or, yes? Oh, you're going back, another one. All right. Probably not. If you have the 9th edition, as long as you do the homework I assign, do you see what I'm saying? So you could actually get copies of the homework from somewhere. I have no idea how different the setup of the chapters are. So there might be sections that didn't exist before, or sections that did and got sucked into somewhere else. Do you see what I'm saying?
Yeah, it was just the only copy that I found at the library.
Oh, really? Huh? They don't have the 10th edition in the library available for like checking out? What's happening?
Nothing, sir.
All right. They should have the 10th edition in the library for checkout still. I don't know if anyone's tried that. Let me know if that's not true, because they should. They did last semester, and we didn't tell them to take it off the shelves yet.
I looked at it on Monday and I didn't see it. Was someone
It's possible. Yeah, there's one more Diffie-Q class out there, so I'll double check with the library, make sure it's actually still there. Anything else before we get into new stuff? You know, or stuff. Okay. Oh, did I bring that? Oh, cool. Oh, this is from before. Okay. I like it. First thing, a couple of things about notation. You guys know, like if I say dot notation, who knows dot notation? You know, like I could come up with something, Jeff. It seems like it would be dot notation, but it has to do with derivatives. Yes?
Don't each dot represent like the number of derivatives?
Sure, exactly. But it's very specifically about derivatives with respect to t. Normally is what is used, and Newton did this. So dx dt, he said is going to be x dot. So you see a lot of these dot notations used in kinematics, right? Study of motion of particles and stuff. Turn this dude off. Go away. So that's one little thing. That's like dot notation. So what do you think x double dot would mean? Yeah, d squared x over dt squared. I like it. So that's one little thing, in case it pops up somewhere in the book, right? And then you've got, what else did I want to say? Oh, this might come up later in the class. This is ODE, which means ordinary differential equations, right? There's also PDE, which means partial differential equation. Oh, shit. Imagine that class. Oh, yeah. But do you guys remember what did, like, FY, you guys remember FY? Or who knows partial differentiation? Anybody? Who doesn't? Who's never heard of partial differentiation? Anybody? So who doesn't like to raise their hand? Okay. Partial f with respect to y there, right? ut would be partial u with respect to t. So this is subscript notation for partials. So, if you're somebody who's got to write these things a lot, you're going to come up, how did you turn yourself back on? Okay, let's become self-aware. I don't want to be off. All right, sure. If you have to write this stuff a lot, you're going to come up with ways to write it quicker, right? And, this notation is always kind of cumbersome, right? Especially when you start getting some higher level derivatives. Okay, so that's a little thing about some notation. I want to make sure you guys had heard of this stuff in case it pops up somewhere. So, we already talked a little bit about some ideas of differential equations. We're going to get into some very specific stuff, ODEs and how to classify them. You can classify them. We just talked about, really this isn't even related to ODEs. Let me just call them Ds. Type would be ODE or PDE, that type of thing. That's a type of differential equation. Is it an ordinary differential equation? Is it a partial differential equation? So ordinary differential equation just means there's only one variable that the derivative is being taken respect to. PDE means there's multiple levels of variables, right? Variables that are dependent on other variables within the problem. And that's 281 if you've taken 281. If you haven't, don't worry, you don't have to. We can do it by whether they are linear or not. Linearity. So we'll talk about that here in a second. We can also do it by order. And order is kind of related to degree. Remember, it's like the degree of a polynomial, right? Like x cubed plus 5x squared. That's a degree 3 polynomial, blah, blah, blah. Order, what takes the place in a differential equation? What takes the place of x now is really going to be y and its derivatives, right? So really the unknown is that function y, right? So order would mean, so this would be a first order diffie q. Yeah, there. You get out of there partial. dy dx plus y equals 2x. Sure. Right, that's a first order differential equation. And amazingly enough, second order, this is first order, a second order would be d squared y over dx squared equals dy dx minus 2y, sure. That would be second order. So much like a degree references the complete exponents in a term, right, for a polynomial. So x squared y would be a third degree term. Order references the degree, the amount of derivatives that have been taken, the highest level of derivative that you're taking of the y. Okay, how are we doing so far? Of the dependent variable, whatever it is. I like it. Sweet. So far not bad. Like I said, chapter 1 is chock full of terminology, so we got to kind of slog through it a bit. So that's easy. Type is easy. Let's talk about linearity. Both of these here that I've written are linear. This is a linear first order, a linear second order. And linear is pretty much exactly what you think. You just have to realize linear in terms of y. So to be a linear differential equation, all the terms involving y have to be a first degree at most, right? And when I say degree, I mean truly power, not this, not order of differentiation. Like I could write a linear first order. Linear first order. Can you guys see that? Poor little dudes underneath there. Linear first order, I can write like this. So to make this like a non-linear first order, I could just put a y squared there, for example, right? You guys cool? Or just anything that's not linear. I could put this over y. I could put sine y. I could square this term. That would be kind of freaky. It's not what we're used to. But sure, I can square dy dx itself. Then that's not linear because there's a y term that's not to the first power of those terms. Let me let that. Yes?
So every derivative has to turn into a number in a sense, right? As you take the derivative, there can't be a y squared, right? It has to turn into a single variable with no raised power.
So, for example,
You
here's
just put either x.
not linear. Let me make sure that everybody sees what I just said. So here's something that's not linear. dy dx squared minus 3x equals sine x, whatever. I mean, that's not linear. Right?
Because
There's
in the sign x.
there's a y piece that's being squared.
Oh.
It's not a linear y piece. So all the derivatives and y itself have to be linear, have to be to a first power.
I guess what I was trying to say is it depends on y, not on x, right?
Beautiful, exactly. See, the x can do whatever the hell it wants to.
Okay.
Thank you, I'm sorry. So yeah, the x can be sine, it could be squared, it could be 1 over x, whatever the hell it wants to. So that's what I meant by linearity. You should have some idea of what linear means. So when we're talking about a linear DE, it's only referencing the y, the dependent variable, has to be linear. The x variable can do whatever the hell it wants to. I like it. Okay. Let's see. What did I forget? And then, if I divide this by whatever the hell this is, and again, that could be the coefficients here and this here could be any function of x that it wants to. It just can't involve y. And you can have this y here. Of course, this could be 0 then, right? So you don't need this term at all. Are you guys with me? If I divide by a1, assuming it's not equal to 0 at key points, I end up with this equation. Same thing, but we just call a0 of x divided by a1 of x, we call it p of x. And g of x divided by a1 of x, what do you think?
X of a.
Q of x, I don't know. I don't know if you've taken 2 anyone, there's p and q, right? I think that shows up. If you haven't, who cares? There it is. It's still the p and the q. So this form, this is a linear first order differential equation. Dude, I like it. So what do you think a linear second order differential equation is going to look like? Starting in this place. And you can see now why I call this a0, a1 with the first derivative, so it's just going to be the exact same thing, except it's going to have freaking a2 in front of a d squared y dx squared, exactly. So it'll be all the same stuff, but with a2 of x plus blah, 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 all the same stuff. So it sort of feels very similar to building polynomials and making it a higher degree. I can build differential equations and make them higher orders. Okay, nothing major here yet, just, new stuff, but nothing crazy. The reason that it's good to take time to talk terminology is because depending on the type of equation you're dealing with, you can have a different method to apply to it. You can maybe imagine that something that's not linear is going to be more difficult, sometimes basically impossible, very often. Let's see, blah, 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 blah. Oh, let me introduce some terminology. Oh my God, what is in here? It's clear, but is it wavy above? No, this is just water. Let me introduce a little terminology early. If this function here is 0, we give that a special name because, and you can imagine, if this is 0, then the process that you should be easier, right? So we call that, if that's 0, note, a little star. If I get a1x, Jeff, it's just a thing that you do. If it equals 0, if g of x equals 0, we call that homogeneous or homogeneous, however you want to pronounce it. homogeneous. So if it doesn't have a 0 here, we creatively call that non-homogeneous. It's amazing. So it's that term, homogeneous, non-homogeneous, is going to come up every now and again throughout the course. And again, it deals with different ways to solve something. I like it. Aw, I like that.
Sorry.
Sounded sort of Hawaiian or something. Okay. So this is just, beginning talking about the different types of differential equations you might have to work with. Let's start talking about the solutions that we might get. So we got this here. I had an instructor once that would be like, and then 4x squared minus 7, and then, he would erase. And no matter, we would tell him not to, and he'd stop, and then he would eventually just creep back up, and he's just erasing. Like, what are you doing? Let's see, where am I? Oh, cool. So here, let me just try to summarize this. Something really key we need to stress right now. When you solve an ODE, what is your solution physically? What is it? When you solve an equation from algebra, your answer is going to be a number. And it could be, a number, a set of numbers, or no solution or something, but it's basically going to be a number, right? When you solve an ordinary differential equation, your answer is going to be a... So let's remember, what did we do? We did this one the other day, right? Remember this? Didn't we talk about this one? Or maybe, did I put a 2 there? Is that what I put there? I think I made it specific. And we talked about why you can just kind of figure this out on its own. It's basically whose derivative is equal to basically itself, and we can figure out where the 2 would come from. Who remembers or can figure out what you should get? Yeah, e to the 2x. And let me see if you guys realize why this should be true. It's actually a constant times that. I didn't make a big deal out of that yesterday. Yesterday relative to the class, in case I say that a lot. Why would the constant not really affect anything? Because it would still be alive here. It would actually cancel out, right? So the answer to an ODE is a function, not just a number. It's a function. Right? The unknown is y. What goes along with a function? Well, Sure. Intervals. Where does it exist? Right? And in fact, the solution to an ordinary differential equation. There's a lot of words that make you sound drunk in that sense. The solution to an ordinary differential equation has to be a function along with an interval over which it is continuous. The solution cannot be something that includes somewhere that it's not continuous. This is going to make a lot more sense when we get to initial value problems. So if I said y of 0 has to be 7, well, obviously you're going to include the part of the problem that is defined around 0, right? So if I had a function that looked like this with some nice asymptotes, and it's like blah, 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 right? And I say y of 0 has to be -2, well then obviously the interval that I'm going to give as part of my answer will be this freaking interval, right? No, and I can't be able to cross this wall because thou shalt not pass this wall. I like it. Little Gandalf. I got a shirt. I'll wear it. At my calc class, some of them took it personally. I'm like, well, maybe you should. I don't know. It's like, thou shalt not pass, Gandalf standing on the asymptote. Okay. Take it personally, you probably should. Let's see, blah, blah, blah. Oh, do I really want to write this formal definition down? Just to show you, because the book uses this symbol a lot. Any function, and you can use a couple different ways to pronounce this symbol, depending on how you feel. Phi or phi. Phi sort of goes with the capital as far as my memory goes, but I've heard phi and phi for this, you know, and then you get giants and shit going in your head, but oh well. Any function phi defined on an interval I, possessing at least, and let me say this up here, solution of nth order, just to make it as general as I can. I don't know if you guys can see that. Solution of an nth order ODE, which means what?
The coefficients can be.
Doesn't talk about the coefficients. Nth order means what? What's a first order mean? First derivative. Second order is the highest derivative I see is second derivative. Nth order means the highest derivative I see is nth derivative. I love it. You're like, whatever, because I don't know what n is. Well, then n. There you go. So solution of an nth order ODE is any function defined on this interval, some interval, possessing at least n derivatives. I mean, a lot of this crap is just, of course it's got to have that many because it's got to be able to be done that many times according to the equation. But yeah, just to make sure you see that. That are continuous on I. No, Jeff, another. Continuous on I. Let me get all this written down so I can talk about lower parts. Which, when, this is really funny, subbed into the ODE works, makes it true. Now notice, I want you to notice a few things. I gave you a little hint about when an IVP comes in about why you have to pick a certain interval. But do you notice how the interval that we're talking about, the derivatives have to be defined, have to be continuous on that interval. So all of these little requirements kind of restrict. So the function itself, the interval on which it's defined and continuous could be large, but then the derivatives might have problems at certain spots, right? And we're going to learn some other things that might decrease this interval size that I could use. So that's why the answer has to always include an interval on which it works. Right? You can't just say the answer is y equals 1 over x. No. It's got to be one of the intervals that's defined on, right? And if it's an IVP, I can tell you exactly which one. If it isn't, you just say 1 over x either on 0 to infinity or negative infinity to 0. All right, let me stop right there. But because the answers we're going to be dealing with are functions, I have to define the interval on which that function does everything it needs to do. Okay, that's a complete solution. Blah, blah, blah. If I find this function, so for this one, and I can't remember, I said y of 0 equals negative 2 or something. Not for this one, yeah. This guy, right? Here's my total, this is my phi graphed totaling, right? This is the answer to some problem, and here's the 3 intervals on which it would be continuous. Are you guys with me? And then if this is the little requirement, then this would be the answer, and this is what we call, remarkably enough, if you give me this picture, this is called the solution curve. Ooh. Because it is specifically the part that solves, it's the curve that solves the IVP, in this case, the initial value problem. I like it. All right, let me stop right there. I'm throwing a lot at you, but yes?
So that whole bottom parabola would be the answer to y.
Exactly. It's the, and I really,
that whole function.
Notice this too. Do you see how I said y is 0 equals negative 2? Because when you solve a differential equation, you're going to get constants C1, C2 just running around. And when you change those, at the very least it's going to change up and down, but it could also change other aspects depending on where it is. So in the case I had up here, it was a multiplier of E. It's going to change the vertical shift, right? Or the vertical stretch. You with me? So if I graph all the solutions with all the values of C, There's a ton of them. This is the one that specifically matches this requirement, right? So yes, this curve meets this, and it works for this, right? So all three of these work for this. This is the only one that works for this and matches this requirement.
So would your interval be negative infinity to infinity?
No. It would be, whatever the hell this
Or
is.
negative.
Let's say this is -3 to 3. Right? So the interval, the I in this case would be -3 to 3.
Okay.
Let me stop there for a second. And again, this is some introductory stuff. Once you start working some problems out, and graphing some stuff, you'll start to really get a grasp of what I'm talking about.
What if phi is continuous?
Say again?
What if phi?
Oh, sure. The interval could be -infinity to infinity for a lot of nice, well-behaved functions, which are a lot of what we've normally looked at. The interval is going to be all real numbers. Yeah,
Okay.
I like it. So hopefully you understand you can have a very well-behaved function whose first derivative is very not well-behaved. Right? I don't know. Can you guys... let's see.
E to the x squared.
Say again?
E to the x squared.
Well, e to the x squared, what happens with its derivative?
2x.
Or are you thinking about the integral?
No, like you said, the derivative will be like something like this.
Yeah, so this is a well-behaved function. It looks nice. The derivative would be...
2x.
This is still not a mean function. So I'm talking about something like... who can tell me what this is probably the... roughly. Sure. Cube root, I love it. So that is a very, very well-behaved function, but its derivative is, and this is not like really badly behaved, but it's a simple function. The derivative is,
Negative.
yes, 1/3,
1/3.
which of course is not defined at 0, because at 0, the slope actually, and that's kind of like what I was trying to change there, but oh well. The slope at 0 is actually,
1.
so like, what's the slope at 0 for a parabola?
0.
0. Now take that and turn it. And I know that one side of it got cranked this way, but it's still going to be the inverse of 0, which is infinity. It gets infinitely big right there.
Oh.
For how long? For infinitesimal second, but that's just enough to screw that up. It's not continuous from -infinity to infinity. Do you guys see what I'm saying? So the function answer might be nice, but the derivatives could screw up the interval that I need to answer with. All right. Something we'll have to worry about soon, and we're not going to start with funky-ass functions that give you a lot of trouble. No, we want to get the ideas and then hit you in the head with the funky-ass functions that give you a lot of trouble. All right, I like it. Okay? But just to give you an idea, I mean, a lot of what they talk about in Chapter 1 are precursors. They don't make all the most sense right now, but they're just trying to lay some groundwork, get some words out there that you're going to see. This is one example of how to look at the interval I, and what could mess that up, what could change that from the answer I get could be something nice, but then my interval can't include places where the derivative is not continuous, right? Okay. Blah, blah, blah. Where did I leave off? I went off on some weird tangent. Okay, I pretty much said that. A little word about... I don't know if you guys remember. Here, just real quick. Can you guys find dy dx for that? I mean, do you guys remember doing this?
Oh, 2y.
What do you have to do to find...
Change it to 4.
No. Oh my goodness. No, I know. It's weird when you get to math and you get all these tools and you're like, all right, when the shit, I got to use this. No, this is just Math 180. This is implicit differentiation. If you don't want to solve for y, you could. You get plus or minus, and you got to figure out how the hell to deal with that shit. But just leave it like it is. How does implicit work? So 2x. This arrow just means this is the method I'm going to use to get this. I didn't put an equal sign because that's freaky. 2x plus
2y
2y,
Yeah, 2 plus 1.
0. I like it. So then dy dx equals, the 2's cancel, subtract x, divide by y. I mean, now notice what just happened. If you did solve for y, and then you took a derivative that way, it feels like you would get two different answers. And you do because this is still implicit. I don't have y written out specifically here, do I? Y is one of two different things. So this is an implicit solution to this. This is a linear. Is this linear? First off, let's start there. Is it? So let me put it. So dy dx. What was the form of a linear? a1x dy dx plus a0x y equals g of x, right? So if it's linear, you have to be able to put it in that form. What do I get? So g of x equals 0, that seems good, right? Here's my function of x. This is a0 of x. a1 of x is 1. But is that linear? No. So on one level, does that really matter right now? No. But I just wanted to check to see if you remember what linear meant. Okay, maybe. Are you guys with me? And of course, we just learned about it a few minutes ago. So you're like, hey, man, back off. But okay. Lost my train of thought. Oh, so this is a implicit solution to this differential equation. So implicit solutions exist. This is not as bad as it can get because I can sort of solve for y. I just have two different answers, right? The upper and the lower parts of the circle. You of course have seen much worse that you cannot possibly solve for y. I don't care how much ambition and hope you got. You ain't going to untangle y from all this shit, right? E to the xy equals natural log of 3x over y plus 7. Oh yeah, have fun with that. You ain't solving for y. But that might be a solution to some differential equation. Okay, so not a big deal. I just want to show you there could be implicit solutions. And just as long as I'm talking about this, everybody's, of course, taken 280. In 280, you learned all the integral things, which is awesome. You learned this trig sub. Remember this stuff? Remember that? You learned, I think you ended with parametric and all that kind of stuff, which is useful. And then in the middle, you might be, not only did you hate it, you're probably like, what the shit was that all about? When you talk about sequences and series, right? But there are differential equations, the only solution for which is a series. There's no single function answer. It is just a series solution, and we will be doing those for damn sure, right? Because that's, to me, the more complete. We're just lucky that some series can be defined in a single, like there's a series for e to the x, there's a series for sine x. But then there's more series than we are able to define functions for. You just got all these series that come out of nowhere that answer certain differential equations that come from real life. So they're useful. And of course, I just go out so much until my tolerance is met, and I say, screw you, rest of that infinite series. That's all I need. All right, maybe. Some of you guys are looking at me like, please start making sense, Jeff. I'm sorry. Okay. Oh, I keep going off in tangents. Where am I? Oh, blah, blah. Oh, yeah, I might as well write this. When you have an nth order ODE, because we're only going to look at ODEs, we're seeking a solution with n parameters. And it will be in this form. Oh my God. I mean, this is just crap. This is just gross. But just to show you, if I have an nth order ODE, you could have up to n constants that you would then need to solve for all n constants for a specific situation. You'd have to be given n initial values and pieces of information. Are you guys semi with me a little bit? All right, so this is just going crazy. We talked about first order, second order. Here's nth order. Oh shit. And then a particular solution. And again, this is going to be a phrase that will just be second nature for you eventually. We're going to get a particular solution, you get a general solution. Okay, great. The particular solution is the form of this with all the C's identified. So no leftover C's, right? No C's. No C's unsolved. Great. No C's left, right? All the constants have been figured out. That would be a particular solution. So just that phrase, on one level, that should be kind of like, wow, Jeff. So if all the C's are 0, that is a particular solution. That's all I'm saying right now. But this phrase will actually take on a bigger meaning to us later in the semester. Okay? Blah, blah, blah. So this is what I meant by it would be, if you've read the first couple sections, you should be doing pretty good with following along. If you haven't, you're like madly writing this out. The first couple sections is just a bunch of definitions, my God. So for me, it would kind of kill me a little bit. I want to get into the meat and start working shit out and getting some answers. Oh well, too bad. We got to do this first. I kind of tried to give a little clue that this type of thing was going to happen, but there's some better examples than what I tried to use just the other day. A singular solution is a solution that you cannot acquire through any value of C. So let me see if I can find a quick example. I mean, there's a few. Here we go. Oh, where'd you go? Here. Okay, here, perfect. Singular solution is a phi that solves the ODE, but no choice of C gets it. Right? You can't choose just a value for C and then that solution comes out. Let me show you an example. But no choice of C creates it. Here's an example. When you solve this differential equation using methods we'll learn eventually. Now, of course, real quick, is this a linear differential? What order is this? No, careful. No. Order is not the same as degree. There's an analogy there. It's first order because order deals with the level of differentiation. Degree of a polynomial deals with exponent type stuff. So this is a non-linear first order differential equation. Shit. If you solve it, you get this. You've lost the solution though, and can anyone see? You always look for what? I mean, basically, you always look to see if 0 works, pretty much. You always look to see if there's a trivial solution. And whenever there's all the terms depend on y equals 0 is going to work. You guys see that? So this is supposed to be the family of solutions, but it doesn't include the most basic solution. Can you come up with a value of C that will make this 0? Hell no. And don't tell me, -1/4 x squared. No, it's not a constant, right? I love it. So I think forever ago somebody told me that. I'm like, well, no. Y equals 0 is also a solution. It's the trivial solution, and it can't be captured by this. Do you guys start to see? So we're going to develop ways to be careful, to not lose a solution just because we got that one, that's the hard, and then, well, shit, we lost that one. It doesn't capture this one.
So you plug that y equation into...
Yeah, if you plug this in here, and I could ask you to verify it right now, but I mean, we were doing that before. That should be the easy problem. In section 1.1, there's quite a few little verify problems, and you should go, yeah, give me a ton of those, right? You should. Differentiation, you should be like, all day, all day, all day. Integration, some days, man. And I understand, I agree, man. Integration is much harder than differentiation. Much. Still going to have to do it. So, just to show you what I was trying to say the other day, is that this captures an infinite number of solutions to like in a kind of like unimpressive way, really. Do you see what I mean? Yeah, C could be anything it wants, so it's an infinite number, but not really. It's one family of solutions, but it misses this entirely. And if you don't know to look for this, you're going to miss it too. Is that always going to be an answer? No. Is that always the example of the answer you're going to miss? No. So we'll have to figure out ways to catch those kinds of solutions. Oh, you'll love this. And again, sort of like I said earlier, I should have said this earlier too. Remember when I was talking about their series solutions, so we're going to have to figure out how to deal with those. There's also possibility of piecewise solutions. Of course, right? We can construct piecewise solutions that fit something. That's a possibility. I like it. That wouldn't be captured by a single expression. Okay. Cool. All right. I love it. Sweet. Okay. We're getting to a point where I can actually ask you to do some problems. So 1-1 really, I mean, has anybody tried 1-1 homework yet? You can. I know a few people have. Right. It's weird. You normally be like, sure, yeah. 1-1 is not hard. It's identify if this is linear or not. Identify the order of this. Verify this is a solution. So 1-1 is a nice intro. Beautiful. 1-2 goes one step further, and it talks about what I was saying earlier, the IVPs. Initial value problem. What's funny to me is sometimes people take a certain amount of physics that get ahead of their math. So, anybody have like quantum mechanics in their future? Anybody? Nobody has quantum mechanics in their future? I'll be all right. Because the next level beyond this is something called boundary value problem. So initial value problem is you identify what y of 0 is. Maybe you identify what y prime of 0 is, depending on how many constants are going to come flying out, how much information I have to give. So it's the initial value at a specific point. Boundary value would be y prime of 0 is pi, and y prime of 3 is 2. So that's boundary problem. And whenever I think about boundary value problems, I think quantum mechanics, because you have a particle in a box, and the box is this long, and blah, blah, blah. You don't the lesser known second life skit, particle in a box. So initial value problem is pretty much exactly what it sounds like. Let me give you, where's example 2? That's a good one. Yeah, here we go. Let me write the general form for you guys. So an initial value problem would be you're given a ODE. I don't think I've written that form yet. Now, in order for it, is this necessarily linear? We don't, because it depends on what little f dude does to x and y. So this is just some first order DE. And I say solve this subject to y of y, get out of there, why not? X naught equals y naught. So like y of 0 equals 3. And very often the input is 0, which kind of goes along with the idea of why we call it initial value. It doesn't have to be, but it could. Most likely it will be. Especially if you're dealing with some science. Now so this is an example of a first order ODE. What do you think has to be true for second order? First off, look at that form there. That's not the most useful form at all for like developing methods to solve something. That The linear form that we put it in is good for knowing how to solve that. And then there's actually a form we could put it in case y is to a certain type of power. You know, but anyway, this is the most general way to write a second order ODE. This is going to involve, bless you, how many, no, it's not exactly this, but can you realize that what's going to happen is there's going to have to be the equivalent of two integrations in a way. Does that by itself make sense? The method we use to solve it might not use direct integration on all the parts of the problem, but there is going to have to be some kind of double integration. That only makes sense. Not directly, so don't get too excited. Which means, how many constants, how many parameters am I going to come out with at most? 2. So I might need to have 2 conditions. So they'll tell me y of x naught equals y naught, and y prime of, in this case, we're going to consider this to be at the same point. I don't know if they made it more general. Good, they did. I love it. Sweet. They shouldn't. Let me stop there for a minute. Okay, I like it. You guys, how are you guys doing? You feeling all right? Feeling a little nauseous? I understand. I think your ODE drama mean. All right, let me see. Blah, blah, blah. Okay, so let's look at this problem here. And of course, we're still at the level where we're not really solving anything yet. We haven't talked about too many methods. Let me give you one. Let me see if I can make one. Oh, this could be exciting, John. I mean, what's the easiest way to make a problem that you guys could solve now? Let me see if you guys can figure this out without me just telling you the type of problem that's easiest to solve. Can somebody tell me, I mean, you can make it unbelievably easy. I mean, there's a problem we could definitely solve now. And let me just, so for example, if I say dy dx equals 3x, and that's the problem. So tell me everything you can about that ODE. It is first order, linear. I like it. That's pretty much all I can tell you. But there's something that, I'm not going to use the name yet because I don't want to get you confused, but do you guys see, let me see if you guys see how to do this. Do you remember, let me do this on the side. Do you remember, you better, integration by parts? What did that involve? Identifying a u and identifying a dv. So dv, for example, you might make it equal to, what does it matter? E to the x, dx. And what did you do then? Yeah, you figured out what d was by integrating both sides. Right? All right, so what if I just... Right? Right, so we're basically doing the thing you've been doing for a long time. They don't even make a big deal of it back then. Right? This is the normal form. Before I wrote the integral, that